Hello, everyone. This is my pleasure to introduce Minghan Ju. Minghan has been here with us in Michigan. He's one of the smart people that I've been fortunate to work with. He always keeps me on my toes for the problems he solves. Today, he's going to talk about equivariant learning for robotic 3D perception.
Okay, so hello everyone. I'm Minghan Zhu, and I've been in Michigan for quite a few years. Actually, when Mane was giving his first iteration of the mobile robotics class, I was one of his students. So it's a great pleasure to come back to this class and give you a guest lecture on this. It's a great honor of me. So I'll get started. Can you see the slides in presentation mode? Okay, cool. So today, the topic of this talk will be equivariant learning for robotic 3D perception. So basically, we are talking about a type of learning framework, and especially in the context of robotics, in robotic perception. So let us start with robotic applications. So we are all in this mobile robotics class, and I think we have a lot of robotic applications in our mind. For example, to name a few, object manipulation, which is basically you have a robot arm or hand to grasp and manipulate objects, a typical robotic task. Or indoor navigation, we have a robot and we want it to move around in an indoor environment, which is also like even existing commercial products on this. And autonomous driving, which has been a very hot field for quite a few years. And we all know it's a very challenging task, and it also can be viewed as a robotic task, like a robot navigating in the outdoor scenario in a very complicated environment. And for all these tasks, 3D perception is an essential part for it. It basically enables the robot to understand the 3D environment. And more importantly, it prepares the robot to interact with the real-world entities in the 3D world. Therefore, 3D perception for robotics applications actually have two very important characteristics. The first is safety critical, because the robot is designed to interact with the real world. Therefore, the errors in the perception can have catastrophic outcome. On the other hand, the computational power for a robot on board is typically limited. Therefore, the perception algorithm is also resource sensitive. We cannot put a huge model like requiring hundreds of GPUs to put it on a single robot. Therefore, these two characteristics of 3D perception for robots poses two requirements on the perception algorithms. The first is having predictable behavior from the perception algorithm is very important. On the other hand, the efficiency is also very important. And here, let us start with the first point. By predictable behavior, we specifically mean we want the perception algorithm to give predictable outcome under various environmental changes. So here, let's break this out and see what composes the environment changes that a robot can face in the real world. Here, I basically put them into two categories. The first is different entities, and the second is different observations. So for the first category, different entities, what does that mean? Basically, for example, for a perception algorithm to recognize a chair, there are a lot of chairs, like different shapes, different styles. And each of them, we want the perception algorithm to recognize them. So there are all kinds of chairs, and we want the model to deal with them robustly. Also, for example, these are the bird's eye view of some indoor environments in the open source data set. Also, of course, there are numerous different layout of indoor environments. Similarly, for the outdoor environments, like the road layout, the environment can also vary drastically. These are all different entities in this context. However, on the other hand, a lot of the environmental changes are coming from different observations of the same entity, the same object. For example, here, if you view a chair from different point of view, the appearance can vary drastically. And the second figure is a tree. You view it from different poses, and the appearance can change a lot. Similarly, for autonomous driving application, the vehicle's appearance can change. Although it is the same vehicle, when it's at different distance to you, the appearance can change a lot. So how do we deal with all these environmental changes? Today, most models basically deal with them in the same way. We just use the large enough deep learning models and design in a very good way. And then we actually deal with all the different entities in different observations. We deal with them in the same way. We just use a model to recognize each of them. However, there's a natural question to ask. Since the different observations are typically, for example, for the same object, then can we only learn once for the different observations of the same object? That is, if a model can recognize the intrinsic property of an object, we know that it is it, no matter what it appears to look like, then what benefit will it bring us? And how do we do this? So here, can we do this? Can we learn once for different observations of the same object? Actually, we can. And the answer is to leverage the symmetry. That is, if the model can capture the underlying symmetry of all the different observations of the same object, this can provide us huge benefit. That is, if we put this symmetry, we deal with all the symmetries in the symmetry preserving models, it can help us to yield predictable behavior for all these observations, because the model knows that it is the same thing, no matter what it appears like. Therefore, it adds a robustness to the perception system. On the other hand, remember that efficiency is also a very important part of robotic perception algorithms. And since now we can deal with all the different observations as the common object, now we can preserve the model capacity to actually learn different entities. And this can reduce the demand on the model capacity to actually grasp the environmental changes in the real world. So here, we say that we want to deal with the underlying symmetry in the environment using the symmetry preserving models, or in other words, we call them equivariant models. So what are they? Here, I will give a brief overview of what this equivariant models means. Basically, equivariance is a property we use to describe a function. The function, if the function preserves the symmetry to some group of transformations G, then we say that this function is equivariant to the group G. In other words, the order of applying the transformation and applying the function does not matter. You can exchange them. Here, the circle notation here denotes the functional composition. So basically, T composed with phi is equivalent to phi composed with T. That means these two operations are interchangeable. The most famous example for equivariance in learning is the convolutional neural networks. They are known to be translation equivariant. So what does that mean? Basically, top you can see there's a figure of a cat. Now, and then we have for example, some segmentation model, phi. And if it's a convolutional network, then the phi model is translation equivariant. It means that the order of applying the segmentation model and applying the translation does not matter. You can either move the cat to another place in the image and apply the CNN model, or you can apply the CNN model first to obtain a segmented mask, and then apply a transformation. The results are equivalent. This is because convolutional networks are translation equivariant. We can see that this property enables a very important benefit, that is generalization over the translational variations of the images. The model does not learn the cat at every position of the image separately. Instead, you learn to segment the cat in one image, and then you move around the cat to arbitrary positions. The model automatically generalizes and knows how to segment the cat. So this is the benefit of equivariant in learning that we all are very familiar with today. However, CNNs are only equivariant to translations. They are not equivariant to rotations. For example, here, if we look at image of a city's bird's eye view, and now you rotate the image, you can see that the output feature map from a convolutional neural network not only goes through a rotation, but the content of the features learned from the image is also changed. Therefore, we know that the translation, the rotation of the input image is not equivalent to the translation of the output feature map. Instead, the feature map, actually, the content is changed. Therefore, actually, the network cannot learn reliable representations when the input goes through these rotational transformations. So that's a bad thing. And here is where the equivariant models comes into the picture. Actually, we can develop an equivariant network that enables the SO2, the planar rotational equivariance. And with a equivariant model, you can see that the input, when the input image goes through a rotational change, actually the output feature map also goes through the exact same rotational change, and the content of the feature map is unchanged, is stable. And here, it enables the network to learn reliable and robust representations from the rotated images. And equivariant networks extends the idea of translational equivariance to more general transformations. And it, of course, it can go beyond SO2 equivariance. It can go to SE2, SO3, or SE3. And we know that they correspond to like the 2D rigid body transformation and 3D rotation and rigid body transformations. So imagine if we have a model that can learn to be equivariant to the SE3, for example, the 3D rigid body transformations. Then here, given two views of the same, like the living room under post changes, the network knows that they exactly correspond to the same layout, the same living room. It will not be confused by the post changes caused by the observer's movement. And this can be very useful for navigation, for example. So this is a big picture of what equivariant models are. And in this talk, I will present you how we can construct such equivariant models. Actually, the equivariant models can be constructed from various network architectures that today typical deep learning community uses. For example, the multi-layer perceptron, convolutional neural networks, transformers, and graph neural networks. We can make all of them equivariant by with certain techniques. And today, we will mostly focusing on the top two, the MLP and CNN cases, since they're relatively simple. We intend this talk to be educational. So we will introduce some relatively simple examples of such equivariant models based on MLP and CNN. And we will introduce very cool applications, the work done by us in our lab and also by other labs, because this is to give you a broader view of what the community is working on in this equivariant learning for robotics in this field. And to make it, and also we will keep the math simple today to just give you a taste of what these models looks like and what they can do, but we will not go into very complicated math details. But actually, this field can be very math heavy because this equivariant model development and the theoretical backgrounds actually can become very can actually require a lot of work in both the math and the engineering part. But today we'll keep it simple. So let's first look at MLP. Without actually introducing a lot of the theoretical backgrounds, we will focusing on a very representative recent work called vector neuron, which is a multi-layer perception work, but it is made equivariant to 3-dimensional rotations. And this work can be applied on point cloud feature learning. And it has been applied in various robotic tasks, including point cloud registration, object manipulation, and SLAM systems, you name it. There are probably more coming out. So I will be introducing this framework to you now. So vector neurons can be regarded as a SO3 equivariant MLP. So we will compare it to what a conventional MLP looks like. A conventional MLP, we take PointNet as an example. This is one of the earliest and simplest, yet still very powerful point cloud learning framework. So for a PointNet, given an input point cloud of, it can be regarded as a matrix of n by 3. So every row is a point. And basically, these different rectangles represent the features for the single point. So basically, for a PointNet, it maps the point feature, a 3-dimensional vector, to a C1 dimensional vector, like it could be longer, and then it maps to some other dimensions. And so every point is mapped to a deep feature independently with Cn dimension at the end. And then we apply, there's a pooling layer to summarize or to basically to get an overview of all the points features to get a single feature vector representing the feature of the whole point cloud. Pretty straightforward. This is what a PointNet looks like. And a vector neuron looks very similar, except that the feature of every point previously it's a n by c matrix. Oh, it's a 1 by c vector. Now the feature for every point is actually a c1 by 3 or c by 3. It added another dimension of 3 dimension of size 3. So every point feature is now a c by 3 matrix. That's the only difference between PointNet and vector neurons on the high level. And why this can be a rotational equivariant network is because notice that there's a length 3 dimension at the end of every feature. Therefore, both the input n by 3 input point cloud and the output c by 3 feature, they can all be acted on by a rotational matrix, a 3 by 3 matrix in the input and in the output. And on a high level, this is what enables the vector neuron to be a rotational equivariant work. I'll break this up step by step and show you how this is achieved. The first step is called feature initialization. Basically to map a point, a XYZ, to a feature. For a conventional MLP, PointNet, it is very straightforward. Basically, it's just by matrix multiplication. Given a 3-dimensional vector, you multiply that by some c by 3 matrix, then you'll get a c-dimensional vector. This is pretty straightforward. For vector neuron, it's a little bit different. Given a vector XYZ, it first actually takes the neighborhood of this point. For example, in this figure, there are 5 neighboring points. So actually, we stack the offset vector of this neighborhood, and then we get a m by 3 matrix for every point. So now you can see that the feature for a point is now augmented to with an extra dimension. Previously it's a vector, now it's a matrix. And then similarly as the conventional MLP, we apply a weight matrix multiplication on the left to map it to some hidden feature dimensions, say by 3. So basically, there's a slight difference between conventional MLP and vector neurons. It's basically there is a step involving neighboring points to lift the dimension of each point's feature from 1-dimensional to 2-dimensional. That's the only difference. After this, actually later parts are pretty straightforward. For example, the linear layer for vector neuron is very similar to the conventional MLP's linear layer, which is matrix multiplication. For a point net, the linear layer is by multiplying the matrix on the left to map a feature vector to another dimension. And for vector neuron, it is done in the exact same way, except that every point, the feature has a extra dimension at the end. However, it is not affected by the matrix multiplication because the weight matrix multiplication is on the left. Therefore, it is the function is of the exact same form, except that the output and input has a one more dimension. And we can check that such a layer is actually rotational equivariant. Remember, the equivariant, the definition of equivariance is just that the transformation and the function is exchangeable. The order is exchangeable. And here we have the transformation denoted by a rotational matrix multiplication on the right. And the function is a weight matrix multiplication on the left. Therefore, it's very easy to see that applying the function first and applying the rotation is equivalent to applying the rotation first and then apply the function, because they all correspond to multiplication on the left and right respectively, and they do not affect each other. So these two operations are equivalent. Therefore, this layer is SO3 equivariant. And also, we can show that the nonlinear layer of the vector neuron is also rotational equivariant. So here, the example is ReLU, the simplest and widely used nonlinear layer in any deep neural networks. For conventional MLP, I think it's very simple. It's just the max of this number and 0. This is what a ReLU does. And for a vector neuron, it is a vectorized version of ReLU. Basically, it first estimates a canonical direction k, which is a 1/3 vector. And then it will truncate every feature, every vector that is on the other side of this canonical direction. And every feature vector that is on the same side in the close direction as the canonical direction will be kept unchanged. So basically, this vectorized ReLU is just lifting this truncation to a higher domain, to a 3D domain, and use a hyperplane to represent the 0 point. And every vector on the one side of the hyperplane is kept unchanged, and on the other side of the hyperplane is projected to the hyperplane, which is the truncation. And it's also very easy to see that this operation is also rotational equivariant, because the whole operation can be viewed as if you apply a rotation on the input, it can be the rotation can be put out of the equation to the right, and therefore it is actually equivalent to applying the rotation on the output of these nonlinear layers. So this is how this nonlinear layers is also made rotational equivariant. Also, the vector neuron is also permutation invariant. This is because the max pooling and average pooling, they are both permutation invariant layer. The idea is basically that you can see that since every point in the vector neuron is processed independently, so the order of you stacking the different point does not matter, because at the end, you always take the max or you take the average. Therefore, the order of all these elements does not matter, will not affect the final outcome. Therefore, this vector neuron, when you apply a pooling at the end, the output is permutation invariant. So with all this property, what can we do? So this is a very nice network architecture. So what can we make use out of it? We know that it is rotational equivariant, and we know it is permutation invariant when we apply a pooling layer. So what can we make use out of it? And here, so this is what we can do. Like, consider a 2-point cloud. The first point cloud is P, and the other point cloud is P prime, which is a rotated copy of the point cloud P with random permutation, where the R is a rotation and the M matrix is a permutation matrix. And we know that we do not know the pointwise correspondence between P prime and P, because we do not know what M is. We just know that they are rotated point clouds, but we do not have point-to-point correspondences. However, due to the equivariant feature and equivariant property and the permutation invariant property, what we know that is that the output of such vector neural network, the SO3 equivariant encoder, will give us the final result that is related by a single rotational matrix. That is, the FP prime equals to FPR. So now this has a very nice property, because given these two metrics related by R, I think we learned in this class that we can apply SVD on these two feature metrics to obtain the final rotation. That is, we can conduct a point cloud registration, but not in the Euclidean space, but in the deep feature space, because the features are related by a rotational matrix. And this is a work that in our lab, we built a point cloud registration work based on this nice property. And how do we do this? I think everyone will all learn how to solve for the optimal rotation given a equation Q prime equals to QR. It's just that the Q prime and Q are not point cloud, but two pseudo point cloud that lives in the deep feature space. So we can first calculate the cross covariance matrix, and then use the singular value decomposition, and then have to calculate the optimal rotation that best aligns the two pseudo point clouds, which are actually deep features. And this strategy is very beautiful, because now we do not need to solve for the correspondences between the 2 point clouds P and P prime. Remember, we do not know the correspondence between the point cloud, but now the deep features are automatically corresponded. They are related by a rotation R, but there's no permutation matrix involved. Therefore, we avoid the need of finding correspondence between all the points. And in practice, we know that P prime may not exactly be a rotated copy of the other point cloud, but they may be corrupted by noise. So therefore, we also train a decoder to train an occupancy decoder to make the feature more robust to noise. And we also apply a loss on the estimate rotation from SVD to encourage the network to find the rotation that actually correspond to the ground truth rotation that we want between the 2 point clouds. And with such strategy, because it is correspondence free, and SVD provides a closed form solution, therefore we can actually conduct a point cloud registration that is independent of the initialization error. Here is a figure that of the registration performance. In the ModelNet 40 is a object CAD model dataset, and we can sample point clouds from the object dataset, and then we rotate the point clouds to different by certain degrees, and then we apply different methods to solve for the rotation. And our method can actually achieve consistent and very accurate registration regardless of the initialization error. So this is what we can do with this equivariant features. It enables us to solve the registration task in a deep feature space in a very simple architecture. And this SO3 equivariant features provided by vector neuron also have other applications by other labs who also have done very cool works. Here are two examples of them. The first is object manipulation. So here the task is that there's an object, for example, a mug, and a robot arm or a robot hand, and then the task is that we show the robot how to grasp a object several times in some poses, and then in test time we ask the robot to grasp the unseen object in out of distribution poses, which is to grasp the marks that are unseen before in unseen poses as well. And here actually the SO3 equivariant features helps because the grasping point can be tracked very reliably under pose changes given the SO3 equivariant feature field. That is to say, in training, you actually mark the grasping point of a point cloud. And then in test time, when the point cloud goes through some rotations, the network can track the grasping point reliably because the features is rotationally equivariant. Therefore, the features also rotates along with the point cloud so that the grasping point can still be tracked on the pose of the object that is unseen in the training. And also another application is SLAM. Here, this work, the new SE work, constructed a object SLAM architecture. That is, in the map constructed by SLAM, the objects are not represented as point clouds. They're represented as SO3 equivariant features. And because we know that the SO3 equivariant features can go through the same rotation as the Euclidean space point cloud, therefore, these features can be fused into the SLAM postgraph optimization. So this is also a very cool work that makes use of such rotational equivariant features. Yeah, so here I introduced a network that is SO3 equivariant based on MLP, and I showed how this can be used in robotics applications. Do you have any questions so far? I think I can also take questions in the middle. If not, I'll continue.
There's one question in chat.
Oh.
Has there been any interest in using SE3 invariant features for place recognition from the similar viewpoints? That's a recent work by Cynthia. I think, yes, I can just quickly say, yes, it will come up. I think, Minghan,
yeah, actually,
maybe explain more, right?
Right. That's a very good point. Question, almost like a question that I will arrange someone to ask in the middle of a presentation. But yeah, actually, sure. So here, actually, this question raises two very important observations. The one is the network we introduced so far is a SO3 equivariant feature. It is not equivariant to translations, which is a limitation. So that's why you see the applications are mostly on objects. And the other side is like for place recognition from these similar viewpoints. So for place recognition that is dealing with point clouds that is larger than object. And that's why we are moving from the MLP, the vector neural work, to a convolutional structure that I will introduce in a minute, because that enables us to deal with a larger point cloud that also presents translational variances. So yeah, exactly. And that's what I'm going to.
Minghan, to clarify, I did not pay anyone to ask any specific questions.
Good.
It's all organic. It's not by me.
Great, yeah. So yeah, that means the students of this class is great, yeah. Asking great questions, yeah. So so let's come to the second part, that is convolutional neural networks. They can also be made equivariant, and as I just said, they can actually augment the SO3 equivariance to more general equivariance, for example, SE3. Then that also enables us to do more complicated tasks, as I will show you. So before I go into the how we can make equivariant convolutions, we need a little bit background knowledge on the concept of groups. So basically, we use groups to describe the transformations. In robotics, all the transformations are actually belong to some groups. A group in math is actually a set of elements, and the set of elements is also encrypted with a binary operator, satisfying the 4 axioms, that is closeness, associativity, identity, and inverse. Basically, these are very easy to understand axioms. Basically, for example, the closeness basically means that if you take 2 elements in the set and you apply a binary operator between them, the output will also be an element in the set. And the identity basically means that there is identity element in the set, so that when this identity, when it is operated on with another element, the return will be the same element with unchanged. So that is what this identity means. And examples are very simple. For example, integers or real numbers, when they are equipped with the addition operator plus, it is a translational group. Basically, just add and subtract the numbers, and they correspond to, you move the, for example, in an R2 plane, this translational group is basically just to move the image contents around in the image plane. So this is a very simple example of a group. And then we also have SO2, SO3, SE2, SE3, the rotations and rigid body transformations in 2D and 3D space. And they are all groups because you apply 2 rotations together, the output is also rotation. You apply 2 rigid body transformations together, the output is also rigid body transformation. So this is just what groups are. The reason that we want to introduce the concept of groups is that they allow us to generalize the idea of convolutional neural networks to equivariant versions. So a conventional convolution is basically given 2 functions. One is f is the input feature map, the k is the kernel or the filter. They are all functions from a Euclidean Rn space mapping to some number. And the convolution between these two, between the function and the filter, is just to take an integral over the Rn space with a translation on the function. So basically, it's an integration over the Rn. The output of this convolution is also a function defined on Rn mapping to some number. So this is what a conventional convolution looks like. And from the last slide, we know that Rn, the Euclidean space, is also a group equipped with the plus operator. So Rn is a group. Therefore, we can generalize this Rn just to groups, to any groups. So then we'll have group convolution. Basically, just to replace every Rn such set to G, which is the group that we care about, or the set of transformations we desire the equivariant property from. So now the function and the kernel filter are both from G to R. And the convolution is also integral over the domain G. And the output feature map is also a function from G to R. Compared with a conventional convolution, a group convolution just lifted the domain for the input function, filter function, and output function, and the convolutional operation. And this G can be Rn, then it maps back to the conventional convolution, or SO to SE3, SU to SE3. For example, we can consider a SE2 case. It is SO2 times R2. And here, because we are doing convolution and they actually need a discretization, we now discretize the SO2 rotation to 4 90-degree rotations. That is 0, pi over 2, pi, and 3 pi over 2. So basically, these are the 4 rotations discretized in the SO2 space. And in this case, actually, what we will see is that the function, the feature map, originally it's defined on the R2 space. And now if we augment that to the group CN of SE2, it will be the function input feature map will be defined on R2 times 4. This 4 element correspond to the 4 element in the C4, which is discretization of SO2. So basically, we augmented the domain. The feature map is now larger. The value now lives not only on a point in R2, but also on a point in the C4 dimension. So this is what a group convolution will look like. The domain is lifted. And because of this, by plug in different G, we can enable different kind of equivariance. For example, I'll give you some application of using SE2 equivariant on images, the 2D translation and the rotations. For example, digit classification. When you rotate the digit on the MNIST dataset, a network can reliably recognize the digit because it is equivariant to the rotations. Now, so it may not be a very funny or interesting application. So there are more complicated ones. For example, object detection in aerial images. Because when you take images from the sky, the object detection task in such data, a very important characteristic is that the objects, it can be of arbitrary orientations. And in such applications, the rotational equivariance can help the network to reliably detect the objects on the ground in different orientations. Also, it can be applied in image key point detection. Here, a model is given 2 images that is rotated copy of each other. And because of this SE2 equivariance, the network can reliably detect the key point and actually corresponds them very well, because the network knows that the features from these oriented key points will be exactly the same as the of the key point before the rotation. And also we can take SE3 and go to 3D space, and it can be applied on point cloud applications. So here are 2. The first is a object pose estimation and reconstruction task. Basically, given a point cloud of the object and put maybe arbitrarily in the 3D world, now a network can detect the object and estimate a pose and reconstruct the full shape of the object under arbitrary pose changes. Also, another work is RGBD 3D object detection, which is in the indoor environment, because the object can be placed in arbitrary rotations. So a equivariant network can detect the object and estimate its orientation very reliably because of the equivariant features. For example, so here is an example of a rotating chair, how it can be dealt with from the using the equivariant model. And there is a even cooler demonstration on their website. So this is also a work from another lab, which I found very interesting. So here, basically, the reference on the left shows the ground truth bounding boxes and the chair that is rotated. And for a non-equivariant baseline, the rotation will cause the network to be confused. It does not know. It will regard every rotated chair as a completely different scenario. So the detection result is not consistent. However, if the model is equivariant, you can see that the detection result is very consistent, and the rotated chair can also be reliably detected with the orientation also estimated reliably. So this is how this group CNN can be applied on more complicated tasks by plugging in different kinds of G into the group convolutional network. Any questions so far? Great, I'll continue.
I ask a question.
Mm-hmm.
So this generalization is very nice. The older solution is data augmentation, right? The non-equivariant methods do data augmentation for all possibility, which blow up the size of training set substantially.
Right.
You comment a little on this factor and when data augmentation outperforms maybe equivariant models, or do we still need data augmentation with equivariant models? Why, if we do?
Okay, so first, if we compare data augmentation and equivariance, so actually this comparison is part of the answer, basically because the non-equivariant baseline is trained with data augmentation on rotations, but you can see that the result is still not as good as equivariant models because the data orientation can only train the network and force the network to learn each instances, each rotations, each different views separately. But an equivariant model can actually deal with them by design. So by design, the network is designed to know that the different rotations are actually of the same object. Therefore, it's much easier to learn and learns more reliable representations. However, do we still need data augmentations? Actually, yes, because the group convolutions, as actually you can see in the previous example, we need a discretization on the group. Therefore, discretization will create gaps in between the discretizations. We still need data augmentations to fill the gaps. However, because now we are just filling the local gaps, the smaller gaps between each discretization interval, that is much easier for the network to learn. Okay, I'll continue then.
Thank you.
Sure. So next, I'll show that actually, so while this group convolution can have various applications and a lot of success, there are some limitations on this group CNN architectures. It's mainly about efficiency. So we can see that the group convolution lifts the domain from some Rn to a larger domain, the group space, a more general domain. It actually will cause the computational cost to increase. Here is a visualization of this. Here I show the conventional CNN and the group CNN in the left and right columns. And the top row is what an element look like. For example, in R3, a point in R3 is just a point. I use a circle to denote it. But now in group CNN, a point does not only have a location, it also have a lot of orientations. For example, now at a point, if we use these 4 directions to discretize the SO3, then at every point, it is a point composed with all the 4 directions. That will create a problem when we apply the convolution, because when we do a convolution, a point will exchange information with neighboring points. In the 3D space for a conventional CNN, for example, here, this point has 4 neighbors, so it will communicate information with these 4 neighbors, do 4 operations with the neighbors. However, for a group convolution, if every point has 4 orientations, and every point has these 4 orientations, therefore, when we communicate the information from this point to the neighboring point, there will be much more connections that needs to build the communications. And you can see every curve here is a curve connecting the orientation of one point to another orientation of another point. And this can cause a lot of computational cost due to the domain lifting issue. Especially when the group is large. For example, SE3 is larger than SO3, is larger than SE2. So that when we go up the dimension, deal with the 3D problems, this computational cost overhead can become a problem. Therefore, one of our work in our lab is to improve the efficiency of group CNN. Our method is to develop the quotient space convolution. So the quotient space, I will explain what is quotient space in the next slide. But the overall idea is just, you can see that the quotient space is denoted as G divided by H. So as typical division, we all know, this division will make the final result smaller. So the key thing we need to know is just that the G over H is a space that is much smaller than the original G. And because we are working on a smaller space, the convolution can be more efficient. So that's the overall idea. And the G over H is the thing we call quotient space. is basically by dividing the larger space by a smaller space, dividing a larger group by a smaller group, and we take the quotient out of it. So we actually developed a quotient space convolution for point cloud processing in our recent work. But actually, the quotient space convolution, this whole idea, the theoretical foundation is actually already built in previous literature. But we bring this property and apply this idea on the point cloud learning in our work. So here I'll explain to you what is a quotient space in the SE3 space. So basically, as you can see that we are working on SE3 equivariance, and we are taking the smaller group H as SO2, which is the circular rotation on a plane. And the quotient space is S2 times R3, which is S2 is the sphere space. Here I'll explain what actually it means. So basically, SO3 is a group of 3D rotations. It can be understood as all the rotations of the ball. And every rotation of a ball can be specified by a rotational axis and the angle around this axis. And by taking the quotient of this SO3 rotation by the planar rotation, it's basically to group all the rotations over the same axis as a single point. So now the quotient space can be represented by all the points on the sphere. So now by removing 1 degree, like that is the rotation around this axis, we go from 6 degree of freedom to 5 degree of freedom. So this is a smaller space. So that's why we say the sphere is a quotient space of SO3 over SO2. And in practice, we work on discretized setup, as we just mentioned. Therefore, the ball SO3 can be discretized as the ball sphere. The ball can be discretized as a polyhedron. Here we are using an icosahedron with 12 vertices. So the rotation, the SO3 rotational group can be discretized into the rotation of the polyhedron that keep all the vertices unchanged. So it can be counted by counting the number of vertices times the number of edges connecting to each vertex. So by rotating the polyhedron by such angles, it will result in the same polyhedron. Like you cannot tell the rotation if all the points are colored the same. And the quotient space, which is the ball, now it's just the vertices of this polyhedron. And for the icosahedron, there are 12 vertices on this shape. So you can see that this quotient operation will take the SO3 group, the discretized SO3 group, from 60 elements to 12 elements, which represent the 12 vertices on the polyhedron. So this is why this operation, this strategy can help us preserve safe computation. And we actually can show that by working on the only 12 dimensional features, we can still recover the 60 rotations of the polyhedron. And this is by permutation. So basically, if we order these 12 vertices in a certain way, we can put them, flatten them into a vector. And every rotation of the polyhedron will result in a different permutation of the vector. And therefore, actually all the 60 rotations will result in 60 different permutations of the 12 vertices. Therefore, even our feature map is only of 12 elements. They can represent 60 rotations by taking the permutations of them. And actually here we show that this strategy brings very huge savings on the computational cost. Here, there are 3 tasks we presented here. They are from 2 datasets. One is a Model 40, which is an object dataset with 3D cat models, which we mentioned before. And the other is 3D Mesh, which is a dataset with real scans of indoor scenarios. And the 3 tasks we experimented here is the post-estimation of the objects, the classification of the objects, and the key point matching in the indoor scenario. And we compare with a baseline that is a SC3 equivariant group CNN applied on point clouds. By applying this Quotient convolution strategy, we can bring down the memory consumption to just a fraction of it, while bringing up the speed in both training and inference to multiple times. Here, the slash is training versus testing. So you can see that in both training and testing, such a strategy can bring huge computational benefits. And with this improved efficiency, we can apply this E3 equivariant learning to larger scale point cloud. And here we are talking about the LiDAR data. They scan the outdoor environment, and they can be of a huge number. And because of the efficiency improvement, we can now apply these equivariant models on this huge data. For example, here is a place recognition work. It's done by one of our lab mate, Cynthia, in a recent work. Actually, it's 2022, but because the publication is 2023, so actually it's the last year core paper. So the idea, the place recognition, probably we've also learned this in the mobile robotic class. It's also called loop closure detection, which is basically when the robot comes to the same place, you know that it is the same place. Therefore, you can associate the observations together to correct a drift and build a more consistent map. And place recognition can be done from images or LiDAR point cloud. But you can see that LiDAR-based place recognition can be more robust to lighting and weather changes. Here, the left figure is a snowy weather with daylight environment, and the right figure is with no snow and captured during the evening. And you can see that the images can vary a lot. However, the point cloud capture in the two scenarios are very similar. So this actually is very helpful for robust place recognition. Then we apply the SC3 equivariant learning on this problem. That is by using this E2PN, the method we just presented, the efficient SC3 point convolution, we can extract reliable descriptor on the LiDAR point cloud viewed from different poses. And here is a visualization of the result. Here you can see that the point cloud goes through different rotations and translations, and the right two figures are the features extracted from the point cloud. The horizontal axis is just it's basically a 1 by 256 vector, and we just plot the vector as a curve. You can see that for a non-equivariant model, the global descriptor can vary a lot when the model when the point cloud is transformed. However, from the equivariant model, because the network is SC3 equivariant, we can extract a very stable descriptor of this point cloud under post changes. I saw a question.
There's a question in chat asking if having SC3 equivariant learning makes the LiDAR-based scan robust.
Yeah, I think so. I think that's so the LiDAR scan is just a still scan. Like the LiDAR, we do not deal with the data. The data is given, but the features learned from the LiDAR scans will be more robust under the post changes because of the equivariance property. The network can learn more reliable descriptors from the point cloud LiDAR scans that is under different viewpoint changes. I hope I answered your question. Yeah, great. So, and also we also have another work also done recently. That is a panoptic segmentation on LiDAR point cloud. So this task is more a semantic, a computer vision task. That is to take sequential LiDAR scans taken by a vehicle, for example, a driving vehicle. And then the target is to provide per point semantic classes and a temporally consistent per point instance ID. So it's basically a combination of semantic segmentation, instance segmentation, and object tracking. Altogether, this is a multitask task on LiDAR point cloud. And in our experiment, we also show that the E2PN, this equivariant learning can enable more accurate object segmentation and tracking, benefiting the overall panoptic segmentation. So in summary, we introduced how to learn equivariant features from some typical network architectures. Here we introduced MLP and CNN. And actually, there are also other ways, like even based on MLP and CNN, there are other implementations and a lot of very good work in this field. And we did not introduce for example, the graph neural networks and the transformers today, but they are also equivariant counterparts of them with different applications. But even only with these two network examples, we've shown a lot of applications in robotics. Here I draw an axis. The left is geometric application, the right is semantic application. And we can see that, for example, the registration and the place recognition, they are on the geometric side. They enable us to learn robust geometric descriptors from the environment. And on the right-hand side, it's the semantic point of view. It can also enable us to, for example, better object detection, better panoptic segmentation. It means that the equivariant learning, although the equivariance is a geometric idea, but because we can separate the geometric variations, the post changes variations out from the learning. Therefore, it also benefits the semantic feature learning for a neural network. Therefore, it can benefit both geometric tasks and semantic tasks. And also, there's somewhere in the middle, actually somewhere in the middle, when we combine the geometric tasks and semantic tasks, it can bring us even more interesting applications. For example, the object SLAM and the grasping work, I think they're very interesting because when you actually combine the robust geometric learning and also combine the semantic learning, that is, you can segment the objects and you know that the same type of objects can have similar feature descriptors. Therefore, when we combine the geometric and semantic part, combine them together, they can be used to build large and useful robotic systems. And this is also, I think, there's a lot of room to explore how we can combine these merits altogether. So what's next? From what we already have today, where can we go like in the future? So here I come back to the figure I showed at the beginning of this presentation. That is, we want to treat the different observations and different entities differently. Like using these equivariant models, we can preserve the symmetry so that we can deal with the different observations reliably with predictable behavior, so that we can save the model capacity to actually learn the different entities. Therefore, a natural way that we want to pursue is want to expand the range of the symmetry of the cases that the symmetry preserving models can deal with. In this way, more variations of the environment can be dealt with in the principled way, and we can reduce the potential number of size of data and size of the model to deal with the other variations, for example, different entities. So for example, other group symmetries. Today, we mostly talked about the rigid body transformations in 2D and 3D, rotation and translations. But there are others. For example, homography, which is the projection of the 3D transformations in 2D. Here, an example is that here we show, for example, a digit 3. All the variations on the right-hand side, you can imagine that as rotating the 3 in 3D space and then map it to the 2D image. And this will cause, like, these variations on the 2D space cannot be explained by translations or rotations. Can we deal with this? If we can deal with this kind of symmetries, that probably can enable even more robust feature learning from image to 3D perceptions. Also, approximated equivariance. This is to say, because the data are actually usually corrupted by noise, and also occlusions. All these factors can result in the data that does not fully obey the equivariance. It is only approximately equivariant. In this way, how do we deal with these situations and recover the equivariance or make use of the approximate equivariance without so when the exact equivariance relation is broken, can we still make use of this approximate symmetry in our models? And the third point, for example, is discover the symmetries from data. Today, our models are mostly we define the symmetries that we want, we desire from the model, and we apply that to the design situation. We know that the network will be equivalent to this kind of transformations. However, this may not always be the case. Sometimes we may want to learn the symmetries from the data itself instead of designing that beforehand. And there are already existing work in this direction, but I think there are still a lot of opportunities in this field. Also, so since we are robotic researchers, so can we find more ways to integrate the symmetries in robotic applications? I think that's even more possibilities to explore in this direction. Yeah, and here is all the figures that I borrow, all the visualizations I borrow from other paper. So here is a acknowledgements to all these papers. Yeah. So do you have any questions? So this is all my presentation today, and all questions are welcome. Thank you.
Thank you, Minghan, for a great talk. Let's see if you have any questions.
Hi, Minghan.
Hi.
I have a question. I have a question for the quotient space you mentioned.
Okay.
How do you come up with the idea that to divide it by SO2 rather than other space like S, just S space? Is
like,
it
So you
yeah.
mean how do we come up with this idea?
Yeah, why do you have the quotient space of SO3 divided by SO2?
Like the choice, why we do the choice. Okay, so actually this is a pretty intuitive idea. So actually it's right, it's correct that we can choose differently. Actually, this idea will also work. Like if you use different subgroups and you calculate the quotient, and you can use that as a space to do convolutional. Here, the idea of using the quotient space of SO2 is actually pretty, because this choice is intuitive. Basically, because if you look at the ball, and the idea is that to describe the symmetry of the ball, we only need the ball itself. We do not need the ball and the rotations around the ball. Yeah. So that's the idea. So basically, because if you want to, so if you look at this, for example, this polyhedron, a human can tell the pose or the orientation of this polyhedron by looking at this polyhedron itself, right? By looking at, for example, here, well, looking at all the colors of these vertices, you can tell which orientation it is. If you always, if you will now define the top as the purple color, and now you just need to find the purple color and the surrounding colors to determine the pose of the polyhedron. So that's all we need. We do not need all the 60 elements. That is, we do not need to rotate it 60 times to tell which one is actually the polyhedron. We only need to look at the vertices. So that is the starting point of why we want to do this quotient representation. That is because we actually can tell the rotations by looking at the vertices of the polyhedron.
Yeah, it makes sense. Thank you.
Yeah, thank you.
I have a question about the correspondence-free paper you did. So you use the decoder to handle the noise, right?
Yeah.
So is it decoder remove out some noise of the features or just used to generate the occupancy field? Because if you have a noise point cloud, then there should be a features from noise.
Yes, you're right. Exactly.
Yeah.
Exactly.
Yeah.
So the decoder is just to help the feature to be more robust to noise. So the idea is, you're right, that if the input, because the input now is just it's not exactly equal to, right? There's an error, there's some noise, and then this noise will be brought into the feature space because of the equivariant property.
Okay. Yeah.
So in this way, there's no way that the feature will be exactly equivariant.
Yeah.
Right.
So how do you handle those features?
Yes. However, you know that although the exact equivariance cannot be achieved because of this equivariant property, actually, because there's input noise, it must be brought into the feature space. However, the features can still be learned. That is, it is not necessary that this guitar will be mapped into this figure. Like this equivariant feature only constrain that they will relate by a rotation, but it's not restricting how the mapping should be. And we know that different such mapping, like if this mapping it maps to a very symmetric pseudo point cloud, that is where you cannot tell the orientations, then the solution can be affected more by the noise. However, if you can encourage the network to learn the feature space that preserves more of the orientation information, then even with the noise, the difference between the estimated rotation and the ground truth rotation can be made smaller.
I see. So decoder is not relevant to the SVD optimization.
No, it's not.
Okay. Yeah,
but it's to basically help shape the feature mapping.
I see.
Be a more useful one.
I see. Thank you.
Sure.
All right, maybe we have time for one more question. I don't see any in chat.
Yeah. I have one more question about Quotient space.
Okay.
Yeah, maybe I didn't understand that perfectly, but so at last we need to describe for one pose to for rotations, right?
Could you repeat your question?
So we have a 12 features in here.
Yeah.
But for one feature, do we need to discretize for the rotations that we did?
Yeah, we did discretize the rotation to 60, which is all the rotational symmetries of this polyhedron.
Do you mean for after we have a 12 features in a Quotient place, do we describe for one features for 5 rotations like we did in a NLP?
Oh, do you mean do we actually discretize the SO2 rotations to 5 rotations?
No, from
So I think if I understand, Dong Young was saying in the beginning, you said for every translation, we augmented the circle features that you discretize. In this case, also every point will have these 12 rotations, right?
yeah.
Yes.
Yeah.
Yes. So every point, because it's SO3 times R3, my understanding is that we'll have this rotation. Maybe.
Yeah.
Do
So
I
every
understand
point.
the question correctly? That's what you asked, right?
Yeah, that's correct. So if we describe from the polyhedron vertices to rotation group, I don't know how it makes the computation efficiency if we discretize. for rotations.
So basically, so if we are using a group convolution, then every point or the point cloud is rotated 60 times, or the filter, for example, the kernel filter is rotated 60 times when applying a filter. And with this quotient representation, we are just rotating the filter or the point cloud 12 times.
Oh, I see.
Yeah.
Okay.
And from the 12 times rotation, although we are only rotating the filter 12 times, but the output feature can be used to discretize, to distinguish 60 rotations. That's the idea.
I see. Thank you.
Yeah, sure.
Okay. Maybe it's a good place to stop. Thank you, Minghan.
Thank you.
Great talk. And thanks everyone for attending the lecture. I'll stop the recording.